This is a black hole. It's a region of space so dense that not even light can escape it. They're extremely curious objects that seem to violate pretty much all of our physical laws, and they may even delete our universe. Stick around to find out how. In this video, we're going to be talking about 5 interesting things you probably didn't know about black holes. Let's jump right into it. Number 1. What would you see if you fell into a black hole? Well, first things first, we have to assume that you're invincible and, don't need any air because you're going to be in space. As you fell in, the first thing you'd see is the accretion disk. It's a spinning ring of really hot matter and gas that's made up of stuff that's falling into a black hole. For example, stars that it's absorbed. As you get closer, obviously the gravitational field would increase in strength. However, this isn't actually always painful. In fact, for many massive black holes, the process of falling in would take several hours, which means that you could just kick back, relax, and watch a couple of Harry Potter movies. As you get closer and closer, the gravitational field would be so strong that it's several times stronger at your feet than at your head. And because of this, you'd actually get stretched into a kind of atomic slurping. The scientific term for this process is called spaghettification. Another really interesting thing that would happen is that if you got a buddy along with you for your ride, they'd actually see you freeze at the event horizon for the rest of the time. The event horizon is the point at the black hole where nothing can escape it because the gravitational field is so strong. You'd also see the entire fate of the universe just play out behind you. And you can see this in this graphic. Number 2, Hawking radiation. Black holes don't actually last forever. They eventually evaporate, kind of like a balloon deflating. The reason this happens is because of quantum processes that happen on the event horizon of the black hole. And the scientific term for this process is called Hawking radiation. Every particle of matter has a particle of antimatter. For example, the electron has the anti-electron. And when they meet, they annihilate each other, leaving behind a lot of energy. Now, a really weird property of space is that sometimes just a random matter particle will pop in and another antimatter particle will pop in and they'll annihilate. And this is fine because they're annihilating each other, so no matter is like being made out of nothing. However, if this process happens near an event horizon of the black hole, you have a matter particle pop in and an antimatter particle pop in. But one of them gets drawn into the black hole, so now you've left this matter particle just created from nothing. So to kind of compensate for this, the black hole has to give away some of its own mass so that the laws of physics are happening. And because of this, once this keeps happening over a long period of time, the black hole eventually radiates away all of its mass. Number 3, supermassive black holes. This is a picture of the center of our galaxy. And this thing inside the blue circle is a supermassive black hole. It's called Sagittarius A star. No need to freak out, however, because the immense size of our galaxy is so big that this black hole is practically nothing. So we're not going to be getting sucked in anytime soon. This black hole is called a supermassive black hole because it's 2.6 million times the mass of our sun. 2.6 million. That's huge. And another really interesting thing is that scientists have discovered at least 13 smaller black holes in that area. According to our predictions, there could easily be thousands of more black holes at the center of our galaxy, and we could use all of these black holes to learn more about the universe. Number 4, accretion disks. We already talked a bit about accretion disks. They're the spinning circle of really hot gas around black holes. They can spin really fast. In fact, some of them have spun at nearly the speed of light, and they can be around 10 times hotter than the core of our sun. One big problem in physics today is that the particle accelerators that we have, although they can go really fast, they can't go quite as fast as we need them to. However, some people say that we can use the accretion disk around the black hole as a sort of natural particle accelerator, and it would be at zero cost to us, and it could go several times faster than what we currently have. Another really cool thing we could potentially do with the accretion disk of a black hole is related to energy. If you watched my previous video on climate change, you would know that we're currently in an energy crisis. We need new renewable resources if we want to cut down on our carbon emissions. There's something called a Dyson sphere. Essentially, it's a giant sphere made up of mirrors that absorbs the energy of everything inside of it. So for example, if we put a huge Dyson sphere around the sun, we could potentially harvest all of the energy that the sun is producing. A theory says that we could make technically a Dyson ring and put that around the accretion disk of the black hole. And we could collect all of the energy that it produces. If we even harvested a tiny percent of that and sent that back to Earth somehow, we could be set for the next few years. And lastly, number 5, the information paradox. It's one of the biggest problems that comes about when we're trying to merge quantum mechanics with general relativity. Take this tennis ball for example. If you look at it, you can see that it's green and is fuzzy. But this is not the information we want to talk about when talking about the information paradox. We want to talk about quantum information, about the atoms that make up the tennis ball. For example, each atom has information about it like velocity, position, and electric charge. Now, a fundamental law of physics is that the total amount of information in the universe has to be conserved. So I can squish and deform this tennis ball beyond recognition, but those individual atoms that are lying on the floor still have information. So this law isn't violated because the total amount of information is still the same. If I chuck this tennis ball into a black hole, the law still isn't violated because even though we can't technically reach out and grab the tennis ball, it's still there. The information is still inside the black hole. The real issue, however, comes about when we talk about Hawking radiation. As you know, the black hole radiates away all of its mass eventually. But what happens to the stuff that fell into the black hole? All of the stars and this tennis ball, for example. Does the information of those atoms of the tennis ball somehow get imprinted onto the Hawking radiation? Like it somehow manipulates the light itself? Or does it get transported into a parallel universe? Well, the thing is, we actually don't know, and this is where the information paradox comes from. If we want to be able to move on in physics and merge quantum mechanics and general relativity, this is one of the biggest problems that we're gonna have to deal with. But that's all for this time, guys. Thanks for watching. If you enjoyed this video, hit that sub and like button and share with all of your friends and family. And I'll see you next time.